So we're going to be looking at kinetic theory today, and it's sort of a way of relating the kinetic energy of particles in a gas with its temperature. Now this is quite a long derivation that you may need to remember for your exam, and just make sure that you can understand and remember each part individually. So first of all, let's say I have a cube and it's of length L. So all the sides of this cube have a length L here. And inside this cube we have a particle, just one singular particle moving at speed u. And what this particle is going to do is it's going to keep moving until it collides with this wall here. And then it will bounce back, and because remember from our first assumption from the previous video, all these particles have collisions that are elastic, so it will move back at a speed of minus u. So the first part of the derivation is, well, the change in momentum is going to be equal to the change in velocity, which is mv minus mu, which is going to be mu minus mu, which is therefore 2mu. So due to this collision, this particle has a change in momentum of 2mu. And we know that speed is equal to distance over time. So the change in time should be equal to distance over speed. Well, the distance that this particle actually travels is from one end to the other and then back again. So it actually travels a distance of 2l, and its speed is u. So the time between each collision is 2l over u. And now we know that the force exerted is equal to the rate of change in momentum. So this is equal to 2mu over 2l over u, which gives you the equation of mu squared over l. And this is the force exerted by the particle in one collision. Now we know that the pressure is equal to force over area, and we know that this is therefore equal to mu squared over L, which is a force, divided by the area, and the area of one of the faces is L squared, because each side of the cube has a length L. So therefore our pressure exerted is mu squared over L cubed. And we know that L cubed is actually the volume of our cube, so therefore we could write this as mu squared over V. So if we rearrange this, we can get that PV is equal to mu squared. So this here actually gives us an equation for one singular particle. But the problem is we don't just have one particle in this volume. We have n number of particles, but they're actually traveling in three different directions. We have n over 3 traveling upwards, n over 3 traveling in the left-right direction, and n over 3 traveling into the page and out of the page. So there are three different directions in which the particles are traveling: up, down, left, right, and into and out of the page. So as we know, this is an equation for one particle. So in total, the pressure exerted on each face is actually given by n over 3 mu squared over v, because there's n over 3 particles hitting each face. So therefore we get PV is equal to n over 3 mu squared. Now in reality, the speeds of our particles will vary. So you're going to have a range of speeds from u1, u2, u3, blah 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 until un. So we need to find a way of averaging out all these speeds. So the way we do this is by using a root mean square speed, denoted by this c with a little hat on top. And it's given by this equation. C is equal to the sum of all the squares of all the speeds, so u1 squared plus u2 squared plus u3 squared all the way until un squared, divided by the number of particles there are, and all of that is square rooted. So this c value here gives us an average of all our speeds. So instead of using u squared, we can now plug in c squared into our equation to get PV equals n over 3 mc squared, where c here is our root mean square speed. Now remember that we also know that PV is equal to nkt. So we can actually equate nkt to n over 3 mc squared. And you'll notice that these n's will cancel. So I can get 3kt is equal to mc squared. And if I were to times both sides by a half, we can see here that I'll get 3 over 2 kt equals half mc squared. And this here is very familiar. This is our kinetic energy equation. So we can say that the kinetic energy of one singular particle in a given volume is given by Ke is equal to 3 over 2 kt. So this means that The kinetic energy of a particle is solely dependent on its temperature. But you have to be careful that this here is only for one particle. So if you had a gas in some sort of volume, the average kinetic energy of a single particle is simply only dependent on the temperature. And that is actually pretty cool. Now, the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously, go and do all the YouTube stuff of liking, subscribing. And if you found this video helpful, feel free to go and watch any of my other ones.